Hi there. I've been working on this custom drone for a few months now, and I want to show you the progress that I'm currently at. We have 4 motors on this PETG housing I have made. The wires go on these little bridges and come up through some holes in the bottom. And inside you'll find a small battery and a PCB. Now there is no microcontroller in here yet because I'm currently working on what's the best microcontroller to use for the drone. However, when it's done, the microcontroller will solder right to the PCB. As you can see, the holes in the sides. Okay, join me as I tell you more about the PCB and how I designed it.
You're looking at the brain of the drone. So this is the PCB, and it has all the components on it that really require the drone to work. One thing that is not on here currently is actually the ESP32, which you'll nest right on top of here, and that's what all these pins are. There's 7 on each side. So the first thing to point out, and one of the most important things, is actually the gyroscope that allows the chip to function, which it allows you to get information such as if the drone is tilted too far one direction because wind's blowing it, and to make the according accommodations inside of the software. So this is actually a MPU 6050 by InvenSense. This is the official. There are a ton of knockoffs you'll find online, and the problem with them is sometimes they have a read or write timeout, which really, it's just an error in the code. And I don't know about you, but I'm not putting that on my drone while it's in the sky. I might fall out. So there's all these things here, like this is the 10th capacitor, there's the 9th one. Here's some big resistors, here's a little tinier one. That was all specified by the datasheet to put it on my PCB with the chip to make it function, and what value to use. So you can just read the datasheet on the chip you're using, and it'll tell you this. That's how I learned how to do it. Okay, so again, this is just a gyroscope chip. It has an accelerometer, and it has a gyroscope on it. Now, really, it measures angular velocity, but we'll go into that more later when I talk about the software. On the back side, we have the JST-I connector. So this is nice power connector. The little batteries I bought actually came with it, so I just put this on there. And I just use 3.7 volt because that's what the ESP32 needs. And the little chip back here can be regulated down to 3.3 volt from the ESP32. So this is a simple motor driver that I got offline. I just did a little research and pulled it offline. So you have one MOSFET, one capacitor, one resistor, one diode per motor driver. If you would have one motor, and you would hook up the positive of the motor here and the negative lead here. They're really tiny motors, so they don't need multiple wires to operate. And then, yeah, so that's basically that. Now let's jump into the software that I used to design it, called EasyEDA Pro. Alright, so this is the software that was used to create the PCB. It's called EasyEDA. I much prefer it. So a lot of people are using KiCad, but I think this is better because it's integrated with a manufacturer, so you can get parts easy. However, on KiCad you cannot. So basically we have 3 parts to our schematic. So the first is going to be our microcontroller. So this is going to be a Zio ESP32S3. I've picked this chip because it's small in form factor, so it weighs little to nothing. And of course it has the built-in Wi-Fi, as do I think all the ESP variants, or at least most of them. So we can actually control our drone over Wi-Fi. Here I have a JST connector that runs power to it. There's this pin 15 and 16, and they have power on the bottom of the Zio, and so that's how we'll actually get power to the ESP and of course the PCB through pins 15 and 16. So I've got some wires coming off. These are to all the 4 motor drivers. So of course there's one motor driver, well, per motor. So it's just a standard motor driver. We have a MOSFET. Most people don't know, or at least I didn't know when I was starting out, but a MOSFET's gate pin actually is like a capacitor. It holds a little bit of charge, and so that is the reason that you always have to pull it down with a resistor. But anyways, on this pin here, and then right here, we would put the the motor. So you just put your positive here, negative here. I'll show you that later in the third dimension, but this is our voltage. These are labels, so we can put the positive voltage here, right? And then of course they're all grounded together. So if we go up here to this is the actual B&O chip, right? The B&O 055 specifically. So this chip is a nice chip. It has gyro, accelerometer, and a magnetometer. Now, magnetometer is only useful if you're measuring, if you're trying to like have a compass for your drone, so you actually know which direction you're at. And this is good if the wind's blowing it, so you can correct, right? You can actually move the drone left or right. It turns out I don't think I'll be using this, but I'm just going to use the chip anyways. It's probably just going to be a bit more expensive, but I mean, it's all wired up here anyways, so might as well, right? So there's so many components on here, right? Capacitors of random values, it seems, and these labels that go out to this complicated stuff. Basically, the datasheet just said to use all this stuff. One of the key things it said to do was to add this, which is right here, a crystal oscillator. So by adding an external crystal oscillator instead of just using the one that's built in, you can actually save on power. We don't have a very big battery, so I just wanted to save as much power as possible without having to do some heavy math and really like precisely calculate how much battery juice we'll have at any given point in time. These are pull up resistors for the data and clock pin. So standard data and standard clock are both used for I2C communication, which stands for integrated, I think. Don't quote me on that. There's also SPI, which is serial peripheral interface. They're just different communication protocols. When it comes down to hardware, you can only have a positive or negative signal. So how do computers communicate? Well, they use a pulse signal, like a square wave, and they adjust the duty cycle and the frequency maybe too. I don't know. Never looked crazy into it like that, but you can of course look more into it. But yeah, that's basically how you know what to put for this. Like, why did I put this here? Because the datasheet said so. And if we go to the datasheet, you can clearly see right here, if we scroll all the way down, that it should say right here, I went too far, right here. So this is the I2C connection diagram. So this chip, right, actually supports I2C, UART, and I guess an HID via the IC, whatever that means. Didn't know HIC was a communication protocol. Maybe it's not. But the I2C connection diagram right here, it tells you all this crap. And now this is kind of a bit misleading because like it doesn't tell you, it just says R pull here, but that's just resistor pull up. And it does tell you, if you read the entire datasheet somewhere in here, it will tell you what's a recommended value, and I chose the recommended value. And also I did check with some other people what they had done with this chip, and that's how I was able to come up with this design I did here. So we're going to test it, of course, in the next video and see if it works. Sorry, this is my editing thing. But we're going to check in the next video, of course, and see if it works. And if it does, go right ahead and copy it, of course, So if we go, let me see, back to my LCSC. Voila. So, yeah, that's how you know where to put these things. So now let's publish this to 3D. Just a minute. Where is it? You do design, update, convert to PCB thing. Now, I did have some troubles routing it on the desktop, so I actually used the one on the browser. I can't remember why. It's just throwing this weird error under this log thing when I use AutoRoute. AutoRoute's great because it saves you a lot of time. So once you've done your schematic, right, like over here, and you've just, again, design, update, convert schematic to PCB thing, you'll get this. And if you go up here to layer, you can see here's top side, here's bottom side. This button right here, whoops, gotta go back to all. Let's go to, this is the top assembly, and here's the bottom assembly. Now this is just a bunch of hocus pocus, right? Let me push to 3D so you can actually see the coolness factor. Look at that. That's a freaking crystal oscillator, man. Is that not cool or what? So these empty pins are what you solder 2 wires to, and then the ESP32 sandwich is on top and does this crazy thing. And so, well, check it out. There is the MOSFETs, the diodes, the resistors, and here's the JSTI connector that we have, all in 3 dimension. Look at that. That's freaking amazing, right? And you can do this yourself too. It's so freaking simple. Yeah. So that is all about the schematic. Okay, so now I'm going to talk about the software. So I am using something called Platform IO. It's kind of like Arduino. It's a like a hardware environment basically. Well, I think it's a toolkit, or sorry, like a what am I saying? I don't know. Anyways, I got the main file, of course, just like any other Arduino project does, right? You write in C++. This code is a work in progress. Okay, we're still trying to figure it out. I'm still waiting for another PCB to come in the mail so I can actually test. If we look up here, the first thing that happens is we have this, well, how do I shift? I don't know how to zoom in on this motherfucker, but check it out. So I have include statements, right? So we had to use like the wire.h. So the wire.h is a library that allows you to basically communicate using I2C and these different protocols like that. That's what that does. Then we have like just these other ones, because I'm using the Adafruit library for the BNO055, right? So I'm using their library to actually read the data from the chip as a, what's it called? As a Euler, because the Euler's in the yaw, pitch, and roll, the degrees that we're needing. So I've defined these constant pins. So like the pin of the front left is motor, pin 4 is what outputs to the front left motor. This is just named badly. Then we have, forgot what, I think this is like the speed of the motors. Anyways, so we define our Wi-Fi stuff. So here's like the password and the actual SSID, which is the name of the Wi-Fi that you can connect to. We have some doubles, which are for our set points, because a PID loop takes in 3 values, a K, P, and I. Sorry, a P, I, a D values, and you tune the 3. And they all affect each other. Well, they all affect different things about the correction. So here I'm just doing a Wi-Fi setup, which is called in my setup function, right? Every Arduino project has the setup function, and that'll run one time on when the program starts. So when I stop the motors, I just analog write 0 to all the pins. So this is a giant web page. This is all the code. You just store it in a variable using these special characters that tell it to treat it as strictly text and not format it, because it's gonna like see the slashes and parentheses and get confused, right? But then in our setup, we just do a serial.begin. So that'll begin the serial on 115.200, the baud rate. We can do our Wi-Fi setup. So a bunch of these are commented out, but you would do BNO begin, you would delay it, then you would get the event. I'd set the original X to the set point X, so it's not trying to accidentally correct and it doesn't like rotate in circles or whatever, right? Because your drone, when you first start it up, you might have it facing north, you might have it facing south, you might have it facing southeast, you know. And then we just loop and we get the event, we set our PIDs, which is like the input X, Y, and Z, right? And then we do some math to get rid of the yaw error for the 360 degrees, because I actually want a negative value. Won't touch on that too much because it's a little bit crazy. Then you have to do the PID dot compute. So this is one PID. This is actually the name of the PID. It's called PID yaw. I have one PID for the yaw, one for the pitch, one for the roll. And you have to do the method compute on it, right? A method is a function of a class. Right? This is motor mixing logic. It might be incorrect. I have to double check on this. But then we do this if true. So if we requested power, right? And of course, this code right here would run inside the actual Wi-Fi, which is way down here, right? So this is all the Wi-Fi. So I'm not going to touch this. I got this Wi-Fi code from the ESP32 example they have, and I just copied it and I expanded on it. So when you check when the text from a packet that's received through Wi-Fi ends with like get/u, because the way it works is when you open the web page on your phone through the IP address of the ESP32 access point, it actually, when you click the button to say tell the drone to fly forward, what's actually happening is it's trying to fetch a page using get/f, right? It's trying to get the page f, because /, as we know, when you go to like URLs, you do /this/that, like www.google.com / whatever it is, So you do the / and then what is after that is the page. So it's trying to fetch a page. So all these are just fetching pages, and it's checking if it's a GET request. And if it's a GET request is like, I'm trying to get something. Well, it's trying to get forward, or it's trying to get down, or it's trying to get down, it's trying to get left, And then you can just print turning left, turning right. And that works if I'm holding it down. And then if it doesn't do anything, because it'll just get hovering and it'll go back. So now I can do it. So if it prints back, then it would set the motors to fly forward, which means it would apply thrust to the motors in the rear. And how would it know to de-apply that? Well, when it's hovering, it would just set all the motors back to the hovering values, right? So that's the idea. And you can do all this in about 317 lines of code. It's a lot, I know, but this has been pieced together. I've forgotten how to do a lot of this. I just did it over the course of a couple months. All right. That really wraps it up. I'm not going to go into detail about the actual drone model. There's not a lot of design that went into that. I just kind of took a caliber and measured the PCB dimensions out and played with the tolerances like crazy. And of course, I'm going to be testing if it's light enough to fly, because you have to power to weight ratio. You know what I mean? It has to be light enough so the motors can lift, plus a little extra so you can actually pick up speed. Otherwise, your drone's going to fly super slow, right? But that's my drone project. Stay tuned for the next update. I hope you enjoyed the video. I didn't try to do a lot of editing on it because I'm garbage at editing and I don't have the money to pay an editor. So if you guys can just like and subscribe, that can hopefully help grow the channel, get me maybe a little bit of income, so maybe I can pay for an editor, get some more visuals going. And yeah, have an amazing day, y'all. Till next time.